Okay, hello everybody. So we're going to talk about the concepts that are needed for roughly, I think, problems 9 through 15. Then after this, we'll be ready for all those problems. So yeah, let's begin. So it'll have to do with volumes and then also equations of lines and planes, which are flat things. First question. What is the determinant of a matrix? Okay, so I have some examples to begin. The determinant of this matrix we just write as det, or det of the matrix. This is a 1 by 1 matrix. It means it's essentially, this is just a real number. I just put it in sort of brackets. It really doesn't matter. So there's no difference between a 1 by 1 matrix and a number. There is a difference when you interpret it later. But anyway, so the determinant of this is just the number. Okay? But what if you have like 4 numbers and you arrange them like this? How do you turn them into one number? Well, so the determinant is a number. And the determinant of this matrix is here, multiply those, minus multiply those. So it's 2 times minus 1 minus 3 times 5. Okay, so that's minus 2 minus 15. So the determinant of this matrix is negative 17. Okay, and now what about the determinant of this matrix? What's it equal to? It should be a number, so it's multiply these minus multiply these. So I get negative 5 halves minus 0. 0 times 17 is 0. Okay, so the determinant here is negative 5 halves. The determinant here was 5. Now a 3 by 3. How do we do 3 by 3 matrices? So this is harder. So what we do is we do multiply these, multiply these, multiply these. Okay, that's hard to see. So first I'll do this one. 1, 5, 9. 1 times 5 times 9. Then I do 2 times 6 times and then wrap around to 7. So that's what we do, 2 times 6 times 7. Then I need to keep going. So, the determinant is going to be a sum. The determinant of this is equal to a sum of 6 terms. It will have 6 terms. Each term has 3 factors, 3 numbers in the term that are multiplied together. We call that a factor. 6 terms because there are 6 things that we'll add. We call those terms. So what are they? It's basically this times this times this plus this times this plus this, this. Now minus this, minus this, minus this. So this is the pattern. Determinants, what are these things? They are something that you will learn about in the class called linear algebra. And determinants are very mysterious. There are many open mathematical questions involving determinants that would make you very famous if you figured them out. So, yeah. But for now, we have to calculate them because for us they will encode volumes. So determinants will essentially give us volumes of objects. And when we're integrating, we'll need to use the volume. And so let's turn this into numbers. 1 times 5 times 9. So these are the 6 terms in the picture, and I'll take this first one and I'll put it here. So 1 times 5 times 9 is here. Plus, now this one becomes 2 times 6 times 7. 6 times 7 plus this one is 3 times 4 times 8. Obviously, when you multiply these numbers, you can do them in any order. Here, now we take a negative 7 times 5 times 3. 7 times 5 times 3. Then we do negative of 2 times 4 times 9. And then we do, last one is negative of 6 times 8 times 1. And this is a number, and that's the determinant. Okay, so the determinant of this matrix is really easy because, well, we start with 7 times 2 times 3 plus 0 minus 0 minus 0 minus 0. And if you'll see in each of these patterns, even if there's just one 0, if you multiply them all together, they're going to be 0. So the only thing that's non-zero is this term. And so the determinant of this matrix is really easy to compute. It's 7 times 2 times 3. 14 times 3. I mean, we can even do this one. 14 times 3 is 30 plus 12. 42. Okay, so those are examples. Now, what is the determinant of a matrix? What is the determinant of a matrix? Well, unfortunately, I will have to leave this as a great mystery. A mystery to be solved in linear algebra. Okay. Which is the most important math class. Because everything gets turned into linear algebra. And that's how we solve PDEs and ODEs, and that's how we solve polynomial equations. And just everything gets turned into linear algebra. In calculus, what do? We take a nonlinear map and we turn it into a linear map, the derivative. So we'll see this soon. Next question. What is the Gram matrix? What is the Gram matrix? Okay, so the Gram matrix, what is the Gram matrix of a list of vectors, or a set of vectors, a list of vectors? So here's a list of vectors. Here's one vector and here's two vectors. Usually I write vectors like this. For some reason I wrote them as columns here. But anyway, they're just two vectors. We can visualize them. Here's the first vector. Here's the second vector. And yeah, what's their Gram matrix? Well, what I do, let's call these vectors v1 and v2. So don't be confused. Like if I say v1 is 2, 1, okay, when I say don't be confused, I mean, I'm sorry, what I just did was confusing. Let me try to make sure that I didn't confuse you. So if I say v1 equals that and v2 equals -1, 3, you might be complaining because usually if I call v equals 2, 1, then I'd say that v is secretly v1, v2, where v1 is the number 2 and v2 is the number 1. But here I'm using it in a different way. I'm just calling, because I had two vectors and I called them both v. So, I mean, then what's this number? It can't be v1. That's the whole vector. So maybe I would say it's v1, 1. And this is v1, 2. Then this would be v2, 1. And this would be v2, 2. And this is just a naming convention. I'm just inventing my own name for these vectors. And there's a couple ways to do it, and this is one way that I chose. Okay, so hopefully that was helpful. Now, if I have these two vectors, v1 and v2, what's their Gram matrix? So their Gram matrix is a matrix where we put v1 dot v1, v1 dot v2, v2 dot v1, which is the same number because it's symmetric, v2 dot v2. So yeah, so this is the Gram matrix. This is a number, a number, a number, and a number. And so it's 4 numbers. And let's just even compute it in this case. So v1 dot itself will be 4 plus 1 is 5. v1 dot v2 is negative 2 plus 3 is 1. v2 dot v1. Remember, what we're doing is we dot these, we multiply those together, and then add the number that we get when we multiply those together. So that's why I get negative 2 plus 3. And you see that it doesn't matter if we flip the names of the vectors. v2 dot v1 is the same as v1 dot v2 because, yeah, just by its definition. So this is also a 1. So this we'd call we'd call it a symmetric matrix, just because this 1 is equal to that 1. And it'll always be symmetric. The Gram matrix is always symmetric because v1 dot v2 and v2 dot v1 are the same number. Now what about v2 dot v2? Let's figure that out. 1 squared plus 3 squared is 10. So this is the Gram matrix. And now, actually, let's take the determinant of this matrix. Then we get 50 minus 1, which is 49. Okay? And what actually ends up being the case is that if then we take the square root of 49 is, in this case, 7. And it turns out that this parallelogram has volume 7. And that is why we care about Gram matrices, and that is why we care about determinants. In fact, you might notice that we could have just taken these two vectors, 2, 1, and negative 1, 3, put them in a matrix, taken its determinant, and we've gotten 2 times 3 is 6, minus negative 1 times 1 is negative 1, and that is in fact 7. So you might say, well, why did we even need to do the Gram matrix? Why didn't we just take the determinant? The determinant would have given us that same volume. But it doesn't always work in higher dimensions. So let's look at this Gram matrix here. Maybe I'll give myself some more room. Okay, so here we are. So these are two vectors. They're somewhere in three-dimensional space. I don't know where they are, but they have a parallelogram that they span too. But this parallelogram is it's flat. So its three-dimensional volume is 0. So it needs another vector to sort of make it into some sort of thing that has actual volume in 3 dimensions. But it doesn't have another vector. It only has these two. So what if I want to find, what is its 2-dimensional volume? Sometimes we call 2-dimensional volume by the word area. What is its 2-dimensional area, or 2-dimensional volume? So over here I just said volume 7, but you might have been more used to the word area 7. But in fact, area is just a special word for a 2-dimensional volume. And here we would say that the 3-dimensional volume is 0, but its 2-dimensional volume should still be some number. How do we find that number? We cannot take the determinant of this matrix because it's a 2x3 matrix, and the determinant only works for square matrices. And you will learn more about that in linear algebra. So all is not lost, because what we'll do is we'll take the Gram matrix. So let's call this V and W. The Gram matrix then, Gram of VW, is a matrix V dot V, V dot W, W dot V, and W dot W. And so let's compute that. So in this case, V dot V is 1 plus 4 plus 9. 1 plus 4 is 5. 5 plus 9 is 14, I think. Okay, and what's W dot W is 49 plus 0 plus 1. That's 50. Now what are these numbers? They should be the same because V dot W is 7 plus 0 minus 3. So that's at 4. Is that right? Okay, and so what we're going to do is the square root of the determinant of the Gram matrix of V and W will be equal to the volume of, actually this is the two-dimensional volume of the parallelogram spanned by V and W. And so, we could take the determinant of this matrix. So the determinant is 14 times 50 minus 16. 500 plus, what's 50 times 4? 200. So this is 700 minus 16. This is 684. Okay, so the square root of 684 is the volume, the two-dimensional volume, aka the area, of this thing. Even though it's very thin inside of three-dimensional space, it's a two-dimensional object, it still has two-dimensional volume, and we'll need to calculate it later when, say, we have some surface inside of two-dimensional space, and we want to calculate, well, that's a weird drawing. I don't know what I'm drawing here. Anyway, it's some kind of surface inside of three-dimensional space, and we want to integrate functions over it. What we'll need is we'll have these little parallelograms everywhere, and we'll need their volume. And so we're sort of forced into this. And, well, this formula, you don't usually learn this formula in calculus, but then you can't do things. You can't do things that you'll need later. You can't do things in higher dimensions until you get this formula. So anyway, well, this is the future, so let's not talk about that. Let's just take the Gram matrix of here for practice. So I'll grab this, move it over here. What's the Gram matrix of this? So let's call this V1, V2, and V3, these vectors. So what is the Gram matrix? The Gram matrix of V1, V2, V3, not W, is the matrix V1 dot V1, V1 dot V2, V1 dot V3, V2 dot V1, V2 dot V2, V3 dot V3, V3 dot V1, V3 dot V2, and V3 dot V3. Obviously, I've messed up. Let's see. This should be V2 dot V3. Okay, let's actually calculate this. What's V1 dot V1? Well, it's 1 plus 4 plus 9. Oh, that's again 14. V2 dot V2 is 4 plus 4 plus 1. Okay, that's 9. V3 dot V3 is 0 plus 1 plus 4. That's 5. V1 dot V2 is 2 plus 4 plus 3. Is that 9? So we can fill in 2 items there. V2 dot V3 is 0 minus 2 plus 2. Well, that's 0. V2 dot V3 is 0, so those numbers are 0. We only have one more to calculate, V1 dot V3, which is also equal to V3 dot V1. So V3 and V1 give me 0, minus 2, and 6. 0 minus 2 and 6 is 4. Great. And so we can calculate the determinant here. It's 14 times 9 times 5 plus 9 times 0 times 4, that's 0, plus 4 times 9 times 0, that's 0, minus 4 times 9 times 4, minus 9 times 9 times 5, minus 0 times 0 times 14 is 0. Okay, so you see that having a few zeros in your matrix really simplifies the calculation. So I don't know, it's whatever these three numbers give you is the determinant. and then the square root of the determinant of the gram matrix equals the volume of the parallelepiped. Yeah, okay. Now, I just want to take a moment. What's the gram matrix of just one vector, v? Say v is equal to 2, 3. In fact, what's the square root of the determinant of the gram matrix of v? If you believe me, it should be some sort of a volume. Well, if there's only one vector, it should be a one volume, so a one-dimensional volume. So what is that? Well, let's just compute it. So what's the gram matrix? It's just v dot v. That's okay, it's a 1 by 1 matrix. V dot v is 4 plus 9 is 13. What's the determinant of that matrix? Well, it's just the number, 13. Remember that the determinant of a 1 by 1 matrix is itself. And what's the square root of that? Well, that's just the square root of 13. And that is, in fact, remember we said the length of v is the square root of v dot v. So the square root of the determinant of the gram matrix is a direct generalization of the length of a vector. And that is why it gives a one-dimensional volume when you only give it one vector. But you can give it more. You can give it 6 vectors inside of 18-dimensional space, and you get the correct 6-dimensional volume of an object inside of 18-dimensional space. So, great.